Okay, thanks. Oh, that sounds better. Okay, thanks. Good morning, everybody. What I'm going to try to do in my presentation is I'm actually first going to introduce you a bit to the FRAM Center in the first half, and then I'm going to dive down into some experimental details in relation to the topics of the workshop. So FRAM stands is an abbreviation for a very long name. It's the Center for Future Chemical Risk Assessment and Management. And as you can see from that photo, we already have our answer, so we know where we want to go. So we are at the moment really trying to sort of develop our questions, the specific approaches where we want to go. So the group that is actually running the center is the usual suspects coming from ecotoxicology, coming from environmental chemistry, coming from statistics, etc. But I think what makes us a bit special is that we are teaming up with people coming from social sciences. So we are having environmental politics experts, we have tax lawyers in there, we have environmental lawyers in there, in order to basically see what are the economic perspectives, the economic consequences, the consequences for social sciences. So how do we act on the things that we are finding? So that's basically one of the ideas behind the Solution Center. And what is driving us is very simple. It's the non-toxic environment, and it's very much the assessment that we had from the Swedish Council. This objective will be very difficult or not possible to achieve by 2020, even if further action is taken. No clear trend in the state of the environment can be seen. And actually you can see a trend, and that's not a very positive trend. Just focusing on pesticides here, because we have a lot of data and we can do a lot of analysis and a lot of time analysis. So here are the analyses from 1988 to 2014. And what we can see, if we're looking just at the risks for the environment, that over the last 7-8 years, the risks for the environment are increasing again. So it's not that we are moving towards the non-toxic environment. The trend is actually not really positive at the moment. From a human health perspective, it's still flat, so there seem to be risk management measures in place that actually keep it on a flat line, but it's actually increasing from a from an environmental risk perspective. And that's basically the main motivation. And the thing is, we have identified 3 types of gaps between what we want to achieve and what we are using and how we are doing that, and I'm just quickly going through that. The first gap is, Werner told that already, so we know that, and I'm not going to go more into details there. It's the mixture issue. That's definitely one thing, and we have a whole workshop to discuss that in more detail. But the other thing is simply that we have a major fundamental gaps between the dynamics of chemical discovery on the one side and chemical regulation on the other side. If we're just looking at chemistry, it's very innovative and they're highly dynamic. We're discovering 70 new chemicals each and every hour. We have around 100,000 of those chemicals in commerce, and we're using around 200 million tons of hazardous chemicals annually in Europe. So this is the challenge. This is what we have to deal with on the one hand. And if we look at how fast and how good we are in dealing with that, before REACH, we managed to assess 200 chemicals when all the environmental authorities, regulatory authorities in Europe were teaming up together. We had just finished a 3-year discussion on whether 3 pharmaceuticals should be classified as priority pollutants, and the agreement after 3-year discussion was, no, we don't really know, let's put it on a watch list. So we don't really do something, we just continue to watch there. We have a never-ending discussion on how we should handle endocrine disruptors. We reached Shakespearean proportions there. The end is really not in sight. If we're looking at what the US EPA is doing, that's a publication a couple of years back in Nature, well, they just have been looking at how quickly has the US EPA finishing assessment reports, chemical assessment reports, and what we see is that over the last years, it was around 5 to 10 per year. And I'm not very optimistic that that's increasing in the near future. So what we see here is really a gap between the dynamic of chemistry and chemical production on the one side and how we are doing things on the other side. That's a nice story. The German Institute for Risk Evaluation and the Environmental Protection Agency have been looking at the data that we have. They have been reviewing 1,800 chemical dossiers that have been submitted to ECHA. The number of fully REACH-compliant dossiers from those 1,814 high production volume chemicals, the number of fully REACH-compliant data sets among those is 1. 1 out of 1,800 is correct. 42% are defined as being complex, basically mean they are so convoluted that you can't really come to a conclusion. 58% showed definite deficiencies. So it's not only the amount of data that we're generating, we also need to be aware of the data quality that is behind it. The third gap is very simple, a conceptual flaw in how we are managing chemicals, and that is that we are basically assuming that our environment is infinite. More chemical production is a good thing. The more chemicals we have, the better it is for society. And I think that's a fundamental flaw that we have to start thinking about. How do we handle that? Let me just give you an example. Every industrial chemical, when we're talking about the regional assessment under REACH, is assessed in an area of 100 times 100 kilometers. So that's the area in which we are assessing a chemical, assuming it is the only compound present. And we have just seen a couple of examples that's far from reality. But the problem is, if we start continuing to think about that, those 100,000 chemicals that we're using require 10 to the power of 9 square kilometers in order to have a sort of safe space. The European environment only has 10 to the power of 7 square kilometers, which basically means our environment is already now 100 times too small in order to accommodate the chemicals in their legally allowed limits in the environment. And of course, new chemicals are coming in. So one possibility that we have is we just increase the size of our environment. Well, I'm not sure that that works, and sorry, I didn't want to zoom on the UK here, that was Outlook. But I think what we have a major gap between how we are approaching things and our aim to actually achieve a pristine and non-toxic environment. So that's the challenge that we're all facing. So I think that basically summarizes that. We know where we want to go. We know that we are not getting there. We sort of have an idea about the direction, but it's a long, long way to go, and things are becoming more pressing by the minute. So we really better get going, I think. So I think that's really the main conclusion. It also ties back to the Sustainable Development Goals that basically people have agreed on, that these are the goals that we should achieving in the near future. The interesting thing is, if you look at that at first glance, chemicals are not there. There is not something with, that even spells out the name chemicals. But if you look closer, they are basically behind everything, from clean water to zero hunger, to life below water, life on land, etc., etc. So chemicals are really also a cost-cutting issue for the global sustainable goals. So again, another motivation to actually start to get a grip on things. What we have been doing is we have been trying to raise awareness on the issue. We have been trying to get involved in the discussion. So what we have been doing is we have been putting a lot of effort to actually start publishing things in the Swedish national newspapers, and most of you are not from Sweden, so I'm going to skip over that. It's basically, the idea is to make people aware that chemicals are a critical issue, that chemicals is something that we have to think about and come up with good ways to handle that. We have been actually having discussions together with people from Parliament, from industry, from the European Environmental Bureau, in order to basically see how can we move things forward. So how do we want to do that? I think we are trying to get to two questions. How can we set productive boundaries for chemical emission? And how can we actually ensure that we have a fair sharing mechanism in place so that we can share the available emission space? So what we basically do is we think about that, we try to implement that in case studies, and then we use that to actually try to refine our concepts. The case studies are starting in Sweden. We plan to go over to the US. We're canceling that at the moment. We're going to Chile because it's easier to work in South America than in North America. And then, if we have the time, go to Kenya in order to work in different ecological systems, but especially also to work in different political systems with different societal expectations, different legal systems, etc., etc. Okay, I want to point out three different issues related to the workshop, and those are not only from FRAM, they are also sponsored by the Swedish Research Council, and of course we are also members of the Solution Project, so it's all over the place. First thing, very briefly only, We have an area of intense activities along the Swedish coastline. We have the biggest chemical industrial cluster nearby. We have been starting to analyze the mixtures there. We basically use exactly the same approaches that we're using in solutions there. These are just the first results, identifying the mixture drivers, identifying those compounds out of the 172 that we analyzed in order to see which compounds are important to have effects on fish, on microbiota, on invertebrates, etc., etc. We are basically facing the same limitations as in all these type of studies. For the coastal environment, I think the critical thing is we don't have clear patterns, we don't have clear gradients, but we have a very widespread blanket of pollution. The general idea that we had is because we have a Baltic current going from the north to the south here, that here we have a pristine site that is then basically going along the industrial areas and then taking the pollutants, and then we have two heavily polluted sites up here. In fact, when we're looking at what we can analyze, and if we're looking at the effect data, there are only very minor differences. We also find a lot of pollution at our pristine site. And that is simply due because the current is in general going in this direction, but depending on the weather, boat current, etc., it's basically just a big mixing area here in the end. I just use that as one example, and that is simply we tend to forget that the Water Framework Directive also covers the coastline. 1 mile into the coast is also the Water Framework Directive. Third example, that's more or less of a theoretical exercise, but the nice thing is that we have pesticide monitoring for the last 15 years or so in Sweden, and it's the same 6 sites that are monitored all the time. So we have around 1,300 analytical samples, and that basically means mixture compositions available to analyze and to see what is the risk in the community, what is the risk that we are basically predicting for the ecosystems. And what we get are the typical waterfall charts, the typical toxic unit summation here. So the most important compound here is MCPA, which is the most common herbicide that we're using in Sweden. We measure a lot of chemicals, but we see that it's only a few chemicals that are driving the toxicity. We also see that the total sum of toxic units here is 10, so the concentration in that river is 10 times higher as the concentration that we are willing to tolerate. But again, or not again, what we see here is actually it's not only 1 or 2 compounds. What we see it's around 10 compounds that really might be defined as drivers of mixture toxicity. But I'm coming back to that in a second. One problem is when you start to analyze those data, you have a lot of values below the detection level. And that is usually something that people say that, okay, we don't see it, we ignore it for the assessment. But if you look at just the ratio between the EQS values for those pesticides, we have them, EQS values and the level of detection, we see that we have certain groups of chemicals here, organophosphate insecticides and perithroid insecticides, where we have up to a factor 100 between the level of detection and the EQS value. Which basically means you go out, you measure the compound, you don't find, and you still don't know whether you have 100 times more in there than what you are willing to accept. So you have absolutely no means in order to basically see, are we there in terms of just the single compounds here? And of course, from a mixture perspective, we have no idea on how to handle that. We don't know what to do with that. It's a fundamental gap in our knowledge, and we need to come up with ideas on how to handle that. And for other compounds, the ratio is better. And for most compounds, we actually have sufficient analytical power to detect concentrations at or around the EQS values. But it's an issue that we need to keep in mind. The interesting thing is if we are then doing the analysis at the 6 sites over from 2002 to 2013, so 10 years. In red here, we have the critical value of 1, where the concentration is just at the maximum where it's acceptable. And what you see is one thing, in most of the sites and most of the samples, it's above 1. And the second thing, and perhaps that's a good example here, what you see is you have a very straight line here. You don't have a trend towards the non-toxic environment or anything like that. It's basically wobbling, but there is no trend that things are going down. And we had new regulations coming into place. We have kicked off certain compounds from the market, etc. It doesn't matter. It doesn't improve the situation in the environment. And I guess for the simple reason, we are analyzing that at the moment, for the simple reason that people are just exchanging pesticides. So one chemical is getting out from the market and they are using another one. And if we're looking at things from a holistic perspective, from a mixture perspective, it doesn't help us. We need to do something else than that. This is the toxic unit distribution of that particular mixture, one of the 1,300. And what we see again here is that we have compounds that are already at concentrations that are, for example, here 4 times higher than their individual quality standard. So those are what we call mixture toxicity drivers at the moment, and those are the obvious choice if you want to do management, risk mitigation. Let's focus on those, because that's a single substance issue here. We can talk about mixtures, but this is really critical. The interesting thing is what happens if we actually assume that this is successful. And this is how it looks when we do that. So here we just assume that we were successful by basically pushing down the toxic unit of every compound just below 1. So each and every compound is present at a concentration that we would assume to be acceptable. So this is a concentration, according to all rules and regulations that we have at the moment, is a situation that we would consider to be safe. But if we are, just because of the sheer number of chemicals, starting to add things up, we are still ending up at a concentration that is 5 times higher than what is acceptable. So single substance-oriented risk management measures really help. It goes down from 10 to 5. But it's something where we are certainly not getting down to the critical value of 1, and this is what we really would like to do in the end. Okay, so just to summarize those 3 case studies, when we're looking at chemical mixtures in coastal waters, we have a diffuse, widespread pollution. It's really hard to find gradients or anything like that in there. Even in highly industrialized areas, at least in Sweden, the pollution situation is actually not too bad. We are around a PEC-PNEC ratio between 1 and 2 in the end, so that is really something that isn't too bad compared at least to the pesticide situation, where we are talking about toxic unit sums of 15 and more. When it comes to the pollution-induced tolerance in Switzerland, I think we can clearly show that the mixtures from the SDP effluents impact microbiological biodiversity and ecosystem services like primary production. We see also that upgrading the sewage treatment plant leads to a recovery of the exposed biology, so it really pays off to do that. And PICT is a means to basically look at the ecological implications of that pollution pattern that we are having here. Pesticides in southern Sweden, we have a substantial risk at all sites, all years, no improvement over time despite new regulations coming in. The single substance-oriented risk mitigation helps. It's really helping substantially to do something, but it's something that is not sufficient alone. We have to go beyond that. We have to really think about how do we handle things from a mixture perspective. And with that, I would like to finish, and thanks for your attention.